I want you to try something. Look at your hand. Really look at it. That hand is made of atoms. Carbon, oxygen, hydrogen, nitrogen. Those atoms were forged in the cores of dying stars billions of years ago. They drifted through space, coalesced into a planet, cycled through rock and water and air for 4.5 billion years. And at some point we can't quite pin down, those atoms became you, became something that could look at itself and wonder where it came from. Now here's a question that will keep you up tonight. What if those same atoms, arranged differently, were once part of another thinking being? Not a human, not even a mammal, something else entirely. Something that lived and thought and wondered millions of years before the first ape climbed down from a tree. What if there were scientists before us, poets before us, civilizations before us? What if we're not the first? This isn't a fantasy. In 2018, 2 scientists at NASA and the University of Rochester asked this exact question. They wrote a peer-reviewed paper about it. They gave it a cheeky name from Doctor Who, the Silurian hypothesis. And their conclusion was disturbing. If an industrial civilization existed on Earth millions of years ago, we probably wouldn't know. The evidence would be gone. Not hidden, not buried, gone. Erased by the same geological forces that erase everything eventually. I need to tell you about time. Not time as you experience it, the ticking of clocks, the rhythm of days, the slow accumulation of years. I mean deep time, geological time. Time so vast that your entire life and the lives of everyone you've ever known and the entirety of human history compresses into a layer of sediment thinner than a sheet of paper. We're not built to understand this. Our brains evolved to track days and seasons, to remember faces and dangers, to plan a few years ahead at most. Geological time breaks us. But let me try anyway. Here's a number: 66 million years. That's how long ago the dinosaurs died. An asteroid the size of a city slammed into what is now Mexico, and the world burned, and the great reptiles that had ruled for 170 million years vanished in what geologists call an instant, meaning a few thousand years. 66 million years. You've heard this number. It's in every dinosaur documentary, every children's book about prehistoric life. But I don't think you've really felt it. Let me try to make you feel it. Recorded human history, everything from the first writing in Sumer to this video you're watching, spans about 5,000 years. If you stacked 5,000 years end to end, you could fit it into 66 million years, 13,200 times. Imagine 13,000 civilizations, each lasting as long as all of recorded human history, rising, flourishing, falling, forgotten, one after another, filling the gap between the last dinosaur and the first human. That's what 66 million years contains. Try another angle. If you could travel back in time 1 year for every step you took, walking at a normal pace, it would take you about 12 years of continuous walking to reach the dinosaurs. 12 years of walking, 8 hours a day, every day, without stopping. That's how far away they are. And yet, in geological terms, the dinosaurs were recent. They died at 11:39 p.m. on the 24-hour clock of Earth's history. We appeared in the last 2 seconds before midnight. Before the dinosaurs? That's where time gets really deep. And the dinosaurs themselves? They ruled for 170 million years. Stack our 5,000 years into that span, and you get 34,000 civilizations. 34,000 rises and falls. 34,000 cycles of discovery and forgetting. 34,000 opportunities for something like us to emerge. Time is deep, deeper than we can really comprehend. And in that depth, almost anything could have happened without leaving a trace. Let me give you a sense of what's in that depth. 600 million years ago, complex animals appear in the fossil record. Before that, life was mostly single-celled, microscopic, invisible. The Cambrian explosion filled the oceans with creatures. Trilobites, Anomalocaris, Pichea, things with no modern equivalent. 470 million years ago, plants colonized the land. Before that, continents were barren rock and sand, baking under an unfiltered sun. Once plants arrived, they transformed the atmosphere, the soil, the possibility of complex life on land. 370 million years ago, our ancestors, lobe-finned fish, crawled out of the water and began adapting to land. The first amphibians, the first vertebrates to breathe air. 300 million years ago, vast coal forests covered the continents. Giant insects, dragonflies with 2-foot wingspans, ruled the air. These forests would become the coal deposits we're burning today. 250 million years ago, the Permian extinction wiped out 90% of all species. The greatest catastrophe in the history of complex life. Whatever caused it, volcanism probably, reset the evolutionary game board almost to zero. 230 million years ago, the first dinosaurs appeared. Small, bipedal, unpromising. Within 30 million years, they would dominate the planet. 150 million years ago, the first birds evolved from small, feathered dinosaurs. The first mammals were already there, hiding in the shadows, waiting their turn. 66 million years ago, the asteroid hit. The dinosaurs died. The mammals emerged from hiding and began filling the empty ecological niches. 56 million years ago, something weird happened to the climate. The Paleocene-Eocene thermal maximum. We'll talk about that. 6 million years ago, our ancestors split from the ancestors of chimpanzees. The human lineage began. 300,000 years ago, anatomically modern humans appeared in Africa. 10,000 years ago, agriculture began. Civilization began. History began. Everything you know as human history, Sumer, Egypt, Greece, Rome, China, the Middle Ages, the Renaissance, the Industrial Revolution, the World Wars, the Space Age, the Digital Age, fits into that last sliver. That last 10,000 years out of 4.5 billion. And industrial civilization, the period in which we've actually left significant geological traces, is about 250 of those 10,000 years. A whisper, a breath, a flicker. Now ask yourself, what else might have flickered in those 4.5 billion years? Let me tell you what a trace is. Right now, you're leaving traces. Your carbon dioxide breath is mixing with the atmosphere. The plastic you threw away last week is sitting in a landfill, slowly fragmenting into microparticles that will spread through soil and water and eventually settle into sediment. The gasoline your car burned left isotopic signatures in the air. The electronics in your phone contain rare earth metals mined from specific geological deposits. Every action you take changes the world in some small way. Most of these changes are invisible, temporary, insignificant, but some of them accumulate. Multiply your traces by 8 billion people. Multiply that by 200 years of industrial activity. What do you get? A layer. A thin, distinct layer in the geological record, marking the moment when one species, us, began transforming the planet at a scale previously achieved only by asteroid impacts and supervolcano eruptions. Let me tell you specifically what's in that layer. Carbon isotopes. When we burn fossil fuels, we release carbon that's been locked underground for hundreds of millions of years. This carbon has a distinctive isotopic signature. It's depleted in carbon-13 relative to modern atmospheric carbon. When scientists analyze sediments or ice cores, they can see this signal clearly. The ratio of carbon-12 to carbon-13 shifts starting around 1850, and the shift accelerates dramatically after 1950. This is called the Suess effect, named after Hans Suess, who first documented it. It's one of the clearest signals of human activity in the geological record. Nitrogen isotopes. Modern agriculture uses synthetic fertilizers produced by the Haber-Bosch process. These fertilizers have transformed the global nitrogen cycle. More fixed nitrogen enters ecosystems now than at any point in Earth's history. The isotopic signature of this nitrogen is different from natural nitrogen, and it's showing up in sediments worldwide. Radioactive fallout. Between 1945 and 1963, nations tested nuclear weapons in the atmosphere. These tests spread radioactive isotopes, plutonium-239, cesium-137, strontium-90, across the entire globe. The fallout layer is visible in ice cores, lake sediments, and soil profiles on every continent. Plutonium-239 is particularly significant because it doesn't exist naturally. Any plutonium-239 in a rock layer must have been created by nuclear technology. This is essentially a "we were here" stamp in the geological record. Plastics. We produce about 400 million tons of plastic every year. Much of this ends up in the environment. Microplastics, tiny fragments of degraded plastic, have been found in every environment sampled: ocean sediments, lake bottoms, soil, Arctic ice, the deepest trenches of the sea. Some of these plastics will persist for millions of years. They'll be compressed into thin films, altered by heat and pressure, but chemically they'll still be identifiable as synthetic polymers. Nothing like them exists in nature. Concrete. Humans have produced about 500 billion tons of concrete since 1900. Concrete has a distinctive mineralogy. It contains compounds like belite and alite that don't form naturally at Earth's surface temperatures. Future geologists will find layers of unusual calcium silicate minerals corresponding to our era. Aluminium. Metallic aluminium almost never occurs naturally. It's too reactive. We've produced about 1 billion tons of aluminium metal since commercial production began in the late 1800s. Much of this will corrode and disperse, but some will persist in landfills and sediments as unusual concentrations of aluminium compounds. Fly ash. Coal combustion produces tiny spherical particles of mineral ash. These spheroidal carbonaceous particles are found in sediment starting around 1850, increasing dramatically through the 20th century. They're a clear marker of industrial activity. Biological changes. humans have caused a mass extinction. Large mammals have been hit especially hard. We've eliminated most of the megafauna that once roamed the continents. The fossil record will show a sudden disappearance of large animals on every continent, correlated with the arrival of humans. We've also introduced domesticated species worldwide. Chicken bones, from the billions of chickens we raise for food, will be one of the most common fossils in our layer. These chickens are morphologically distinct from wild birds, bred for enormous breast muscles and rapid growth. Future paleontologists will puzzle over this strange, deformed bird that appears suddenly in the fossil record in vast numbers. We've transported species across oceans. The global homogenization of flora and fauna, rats and cats and dandelions appearing on every continent, will leave a distinctive pattern in the fossil record. All of these traces are real. They're measurable. They're being studied right now by geologists who want to define the Anthropocene. But here's the thing. How long will they last? The carbon isotope signature will persist for millions of years. It's baked into carbonate shells, coral reefs, and marine sediments. As long as those rocks exist, the signal exists. The plutonium will decay. Plutonium-239 has a half-life of about 24,000 years. After 10 half-lives, about 240,000 years, less than 1,000th of it will remain. After 1,000,000 years, it'll be almost gone. But the daughter products, the isotopes it decays into, might still be detectable as anomalies. The plastics will transform. Heat and pressure will alter their chemistry over millions of years. But the molecular fragments might still be recognizable. Long-chain polymers that don't match any natural organic compound. The fly ash will persist indefinitely. Inorganic mineral particles don't decay. They might be dispersed, eroded, buried, but they'll remain as tiny spheres of unusual composition scattered through sediments of our era. The biological changes will be clear in the fossil record, as clear as anything can be in the fossil record, which is never very clear. The mass extinction, the appearance of domestic species, the global redistribution, these will be visible to future paleontologists. So we leave traces, real, durable traces. The Anthropocene will be detectable for millions of years. But will it be interpreted correctly? That's the question. That's what the Silurian hypothesis asks us to consider. If you handed a geologist a rock sample from 60 million years in the future, a sample containing our layer, and you didn't tell them anything about us, what would they conclude? They'd see a carbon isotope excursion, a sudden warming event, a mass extinction, unusual chemical signatures, and they'd probably conclude volcanic eruption, or maybe asteroid impact, or some other natural catastrophe. Because that's what these signatures usually mean. That's what they've always meant, as far as we know. The thought that a species of bald apes with opposable thumbs had built cities and written symphonies and split the atom, that thought wouldn't even occur to them. Why would it? There would be no cities, no symphonies, no reactors, just chemical anomalies in the rock. This is the heart of the Silurian hypothesis. Our civilization, which feels so permanent, so monumental, so important, it's actually a gossamer thing, a whisper in the geological record. Given enough time, it could be mistaken for a volcanic burp. And if that's true for us, it could be true for others. I need to tell you what happens to a city when nobody maintains it. Pick a city, any city. New York, Tokyo, London, Sao Paulo. Imagine everyone vanishes tomorrow. Not a war, not a plague, just gone. The city is left exactly as it is, but no one is there to take care of it. Day 1. Nothing visible changes. The lights stay on for a while, running on automated systems. Traffic lights cycle through their patterns for nobody. Week 1. The power grid fails. Without human operators to balance load and manage faults, substations trip, generators shut down. The city goes dark. Refrigerators stop. Food begins to rot. Month 1. Water systems fail. Pipes burst in buildings where temperatures drop below freezing. Basements flood. Mold begins to grow. Rats and cockroaches feast on the rotting food. Dogs and cats, trapped in apartments, mostly die. The ones that escape form feral packs. Year 1. Vegetation begins to reclaim the streets. Grass pushes through cracks in pavement. Vines climb walls. Tree roots probe into foundations. Without heating in winter, pipes freeze and shatter throughout the city. Buildings begin to suffer water damage. Decade 1. Wooden structures are failing. Termites, fungi, and rot have weakened them. Roofs collapse. Fires, sparked by lightning or chemical reactions, burn unchecked through neighborhoods. The first steel structures show serious rust. Paint is peeling. Glass is cracking. Century 1. Most buildings have collapsed or are structurally unsound. The steel skeletons of skyscrapers still stand, but they're rusted shells. Bridges have fallen. Streets are forests. The only structures that look intact are stone buildings in dry climates, churches, monuments, a few government buildings. Millennium 1. Even the stone is weathering. The skyline is unrecognizable. What was once Midtown Manhattan is now a hilly forest with some unusual rock formations. Archaeologists of the future might find artifacts, glass, ceramics, some corroded metal. But the pattern of the city is gone. You couldn't reconstruct the street grid from what remains. 10,000 years. The layer we call our civilization is now a stratum of unusual debris, a meter or two thick, buried under accumulated sediment. Excavation might reveal that something unusual happened here, but what? An ancient garbage dump? A natural mineral deposit? A meteor impact site? 100,000 years. Continental ice sheets have advanced and retreated, bulldozing the landscape, grinding buildings into gravel, mixing the debris of Manhattan with the debris of 100 kilometers in every direction. Our layer is still there, but it's scrambled, dispersed, diluted. 1,000,000 years. Geological processes are reshaping the region. Erosion is carrying our remains toward the sea. What doesn't erode is being buried deeper, compressed, heated. The plastics we made are becoming thin films of unusual carbon. The metals we refined are oxidizing, dissolving, reconcentrating according to geological rather than human logic. 10 million years. Plate tectonics is rearranging the map. The Atlantic is wider. Coastlines have shifted. The sediments that contain our remains are being folded, faulted, partially subducted. Some of what we made is now deep in the earth, heading toward the mantle. Some is exposed on the surface, weathering into dust. 100 million years. This is the timescale between us and the dinosaurs. On this scale, almost everything is recycled. Ocean floors are created and destroyed. Mountains rise and erode. Continents drift, collide, break apart. If anything remains of us at this point, it's a faint chemical signature in certain rocks, an isotope ratio that's slightly off, a concentration of rare elements that doesn't quite match natural patterns, a thin layer of microplastics transformed by heat and pressure into something almost unrecognizable, a whisper, a ghost, a might have been. This is what the Silurian hypothesis is really about. It's not about lizard people or ancient aliens or any of that nonsense. It's about the fragility of legacy, the impermanence of even our mightiest works. We build for the ages, but the ages are longer than we imagine. Let me tell you about the Paleocene-Eocene thermal maximum. 56 million years ago, something happened. We're not sure what, but the results are clear. Over a period of about 20,000 years, global temperatures spiked by 5 to 8 degrees Celsius. The oceans acidified, species went extinct, the climate system went haywire. This was one of the most dramatic climate events in the past 100 million years, and we're still arguing about what caused it. The signature in the rocks is unmistakable. There's a sharp negative excursion in carbon isotopes, meaning a sudden release of carbon that was depleted in the heavier carbon-13. There's evidence of warming in fossil plant distributions and oxygen isotopes. There's evidence of ocean acidification in the dissolution of carbonate shells. The amount of carbon released was enormous, somewhere between 2,000 and 7,000 gigatons. For comparison, humans have released about 2,000 gigatons since the Industrial Revolution, and we're on track to release thousands more. Sound familiar? It should. We're doing the same thing right now. Burning fossil fuels releases carbon that's depleted in carbon-13 because it comes from ancient plants that preferentially absorb the lighter isotope. This causes warming. The oceans absorb carbon dioxide and acidify. The Paleocene-Eocene thermal maximum looks, in broad strokes, like an ancient version of our climate crisis. What caused it? The leading hypothesis is volcanism, massive eruptions in the North Atlantic as Greenland separated from Europe. These eruptions formed a feature called the North Atlantic Igneous Province, one of the largest volcanic events in the last 200 million years. The eruptions released carbon dioxide directly, but that's not enough to explain the total carbon release. So scientists think the volcanism triggered additional releases: methane from ocean sediments, carbon from burning coal and organic matter that the magma intruded through. It's a reasonable hypothesis. The timing fits, the geology fits. Most scientists accept some version of this explanation. But here's the thing. The exact mechanism remains unclear. We can't fully account for all the carbon. The rate of release is debated. The sequence of events is uncertain. Schmidt and Frank made an interesting point. If we were looking for an ancient industrial civilization, the PETM is exactly the kind of event we'd expect to find. A carbon isotope excursion, rapid warming, ocean acidification, mass extinction. They're not saying the PETM was caused by an ancient civilization. There's no evidence for that, and they're careful to say so. The timescale is wrong. 20,000 years is too long for industrial activity as we know it. And there's geological evidence supporting the volcanic hypothesis. But they are saying that if such a civilization existed, This is what its signature might look like, and we might have already found it and attributed it to natural causes. That's unsettling. How many other natural events in Earth's history might have sapiogenic origins that we'd never suspect? Consider some possibilities. The Permian-Triassic extinction, 252 million years ago. The worst mass extinction in Earth's history. 90% of all species died. The cause? Probably massive volcanism in Siberia. But what if that volcanism was triggered or amplified by industrial activity? We'd never know. The traces would be too faint, too old. The late Devonian extinction, 370 million years ago. Multiple pulses of extinction over millions of years, killing much of marine life. The cause? Uncertain. Ocean anoxia, maybe. Climate change. We're not sure. Could any of it have been industrial? Probably not. Complex life on land had barely gotten started. But the uncertainty is revealing. The Eocene-Oligocene extinction, 34 million years ago. Dramatic cooling, Antarctic ice sheets forming, major changes in marine ecosystems. The cause? Probably tectonic. The opening of the Drake Passage allowed circumpolar currents that isolated Antarctica. But there are mysteries here too. Timing questions, carbon cycle anomalies. None of these events were likely caused by ancient civilizations. I want to be clear about that. The scientific evidence points to natural causes, and extraordinary claims require extraordinary evidence. But the Silurian hypothesis makes a methodological point. We're not looking for civilizational signatures. When we find a mass extinction or a climate anomaly, we assume natural causes because we've always assumed natural causes. We have a blind spot. If we wanted to test the Silurian hypothesis seriously, we would look at these events differently. We would ask, what chemical signatures would an industrial civilization leave that volcanism wouldn't? Synthetic polymers, transuranic elements, unusual concentrations of rare earth metals. We haven't looked for these things. Not because the idea is crazy, but because it never occurred to us. Maybe it's time to look. Let me tell you about dinosaurs who might have been people. I don't mean people like us. I mean beings with minds, language, tools, culture. Beings who could have looked up at the stars and wondered. There was a dinosaur called Troodon. It lived in the late Cretaceous about 75 million years ago. It was small, about the size and weight of an adult human. It walked on two legs. It had forward-facing eyes for stereoscopic vision. It had grasping hands with partially opposable digits. Most importantly, it had a large brain. For its body size, Troodon had one of the largest brains of any dinosaur. Not human-sized, certainly, but larger than you'd expect. Comparable to modern birds, actually, and we know how smart corvids and parrots can be. Paleontologist Dale Russell, in the 1980s, published a speculative paper asking, what if Troodon's descendants had continued evolving for another 66 million years? What if the asteroid hadn't hit? He created a hypothetical creature called the dinosauroid, an upright, big-brained descendant of Troodon that looked eerily humanoid. It was a thought experiment, not a scientific prediction. Russell was illustrating how evolution might converge on similar solutions for similar problems. The dinosauroid was controversial. Some scientists criticized it for being too anthropocentric, assuming that intelligent beings would look like us. Others pointed out that evolution is unpredictable. There's no guarantee that larger brains would have evolved at all. But the underlying question is valid. Dinosaurs ruled for 170 million years. During that time, did any of them evolve intelligence? We assume not. The fossil record shows no obvious signs of civilization. No dinosaur cities, no dinosaur tools, no dinosaur art. But let's think about this more carefully. How many dinosaur fossils do we have? Thousands. Maybe tens of thousands. But dinosaurs existed for 170 million years, and at any given time, there were millions of individuals alive. The fossil record captures a tiny, tiny fraction of the animals that ever lived. For an individual animal to become a fossil, it needs to die in very specific conditions. Rapid burial in fine sediment, away from oxygen, where mineralization can occur. This happens rarely. Most animals are eaten, scattered, decomposed, recycled. We estimate that less than 1% of all dinosaur species have been discovered, probably far less. There were dinosaur species that lived and died and never left a single fossil. If one of those species was intelligent, if there was a dinosaur civilization, would we know? The civilization wouldn't leave fossils in the normal sense. Fossils are bones and teeth, and intelligent beings don't have notably different bones. A human skeleton, without context, looks like an unusually gracile ape. A troodon skeleton looks like a small theropod. Intelligence leaves no obvious mark on the skeleton. Tools? Tools made of stone might survive, but stone tools look like stones. Until you know to look for them, you might miss them. And 80 million years of geological processes would scatter, erode, and transform any stone tools beyond recognition. Structures? Wood rots. Bone dissolves. Even stone structures would be ground down by erosion over tens of millions of years. The only traces would be subtle. Chemical signatures in sediments, changes in ecosystem structure. Maybe, if we're very lucky, something that looked like deliberate burial or artifact caching. We haven't found any of these things, but we also haven't looked. Paleontologists aren't trained to look for signs of civilization. They're looking for bones and teeth and trackways. The possibility of intelligent dinosaurs simply isn't on their radar. And here's the thing. Even if there were intelligent dinosaurs, they might have been very different from us. They might not have used fire. Dinosaurs were probably warm-blooded, or at least something close to it. They didn't need fire for warmth. And cooking food, while helpful, isn't strictly necessary for survival. Without fire, they wouldn't have developed metallurgy. Without metallurgy, no industrial revolution. No machines, no electronics, no cities of glass and steel. Their civilization, if they had one, might have been made entirely of organic materials. Wood, bone, plant fibers, that wouldn't survive geological time. They might not have had agriculture. Some intelligent species might remain hunter-gatherers indefinitely, especially if they're apex predators in a productive environment. Why farm when you can hunt? Without agriculture, no permanent settlements, no cities, no dense population that leaves clear traces. They might have been aquatic or semi-aquatic. Some theropod lineages were adapted to coastal or riverine environments. An intelligent aquatic dinosaur wouldn't build in the same ways we do. Water erodes differently than air. Aquatic structures would be even less likely to survive. The point is, that we're looking for our kind of civilization. Big buildings, metal tools, permanent settlements, modified landscapes. But an intelligent species might develop differently. They might leave traces we wouldn't recognize, or no traces at all. Now, let's be clear. There's no positive evidence for intelligent dinosaurs. This is speculation, not science. The simplest explanation for the absence of evidence is absence of intelligence. But the Silurian hypothesis asks us to be humble about our certainties. We don't know what we don't know. The fossil record is incomplete. The geological record is fragmentary. Our assumptions about what intelligence looks like might be parochial. Maybe dinosaurs never developed intelligence. Probably they didn't. But probably is not certainly, and the difference matters. Let me extend this to other lineages. Cephalopods, the group that includes octopuses and squid, have been around for almost 500 million years. Modern octopuses are remarkably intelligent. They solve puzzles, use tools, recognize individual humans, appear to play. Their brains are structured completely differently from ours. Most of their neurons are in their arms, but they achieve sophisticated behaviors nonetheless. Could ancient cephalopods have developed intelligence? Underwater civilizations wouldn't look anything like ours. No fire, no metallurgy. But that doesn't mean no technology. Biological technology, selective breeding, bioluminescence manipulation, ecosystem engineering might be possible without fire. What traces would an ancient cephalopod civilization leave? Maybe changes in the distribution of shells, indicating selective harvesting. Maybe unusual concentrations of certain minerals, indicating deliberate accumulation. Maybe structures that look like coral reefs, but have unusual patterns. We haven't found any of these things, but again, we haven't looked. Synapsids, the ancestors of mammals, dominated the Earth before the dinosaurs, during the Permian period. Some were large, sophisticated predators with relatively large brains. The Permian lasted about 50 million years. The Permian ended with the worst mass extinction in Earth's history. Whatever existed then was mostly wiped out. The survivors gave rise to the mammals and the dinosaurs, but the Permian itself is a dark age, poorly understood. Could intelligent synapsids have existed? The fossil record from the late Permian is sparse. The extinction was so severe that most evidence was destroyed. If there was a Permian civilization, it would have been erased twice over, once by the extinction itself, once by the hundreds of millions of years since. I keep saying probably not, and that's important. I'm not claiming any of these things happened. The most likely scenario is that we're the first intelligent species on Earth. But the Silurian hypothesis forces us to admit that we can't be sure. The past is deep and dark and mostly lost. Things might have happened that we'll never know about. And if that's true for Earth, it's true for every other planet in the universe. The cosmos might be haunted by forgotten civilizations, ghosts we'll never see, whispers we'll never hear. Let me tell you about erasure in more detail, because it's the key to understanding why ancient civilizations would be invisible. The Earth doesn't preserve history. It destroys it. Continuously, systematically, thoroughly. The processes that shape our planet are also the processes that erase the past. Erosion. Rain falls, rivers flow, Wind blows. Glaciers grind. Every year, these processes remove about 21 billion tons of sediment from the continents and carry it to the oceans. Mountains are worn down to hills, hills to plains, plains to sediment. A building left untended will be eroded. First the sharp edges go, then the details, then the bulk. Give it enough time, a few million years, and it's a pile of rubble indistinguishable from natural rock. Give it more time, and even the rubble is gone, washed to the sea. Burial. Sediment accumulates, layer upon layer, year after year, era after era. What's on the surface gets buried. What's buried gets compressed. What's compressed gets heated. The weight of overlying rock transforms everything beneath. A layer of microplastics, buried under kilometers of sediment, will be squeezed and heated. The polymers will break down, reform, transform. After tens of millions of years, they might still be detectable, but they won't look like plastics anymore. There'll be strange organic compounds in the rock, requiring careful chemical analysis to identify. Subduction. At the edges of tectonic plates, ocean floor dives into the mantle. This process recycles the ocean floor completely every 200 million years or so. Whatever's on that ocean floor, sediments, fossils, artifacts, traces, goes down with it. Material that's subducted gets heated to thousands of degrees, melted, mixed with mantle rock, eventually returned to the surface through volcanism. But it returns as magma, not as the objects it once was. The information is destroyed. This means that any traces on ocean floors older than about 200 million years are simply gone. If there was a civilization 300 million years ago that left traces on the ocean floor of their time, those traces no longer exist. They were subducted, melted, recycled. Metamorphism. Deep burial changes rocks. Heat and pressure transform minerals, destroy fossils, erase fine details. A rock that was once sediment becomes schist, gneiss, marble. Beautiful rocks, but rocks that have lost their original information. Chemical signatures might survive metamorphism if they're robust enough. Isotope ratios, for instance, can persist through melting and recrystallization. But delicate traces, the shape of a fossil, the pattern of a tool, are destroyed. Weathering. At the surface, rocks are attacked by air, water, and life. Minerals dissolve, metals oxidize, organic matter decomposes. Even the most durable materials are slowly broken down. Granite, one of the most durable rocks, weathers at a rate of about 1 to 5 centimeters per 1,000 years in temperate climates. Over 1 million years, that's 10 to 50 meters of granite eroded away. Over 100 million years, that's entire mountains worth of granite gone. Diagenesis. When sediments are buried, they undergo chemical changes. Water is squeezed out, minerals precipitate, organic matter is transformed. The original sediment becomes rock, but in the process, much information is lost. A dead organism falling to the ocean floor will be buried by sediment. As the sediment accumulates, the organism is compressed, its soft tissues are destroyed by bacteria, its hard parts are dissolved or replaced by minerals. What remains is a fossil, a shadow of the original, preserving some information but losing much more. Now imagine an artifact, a tool, a piece of technology going through the same process. The original materials are transformed, replaced, dissolved. The shape might be preserved, or it might not. After 100 million years of diagenesis, would you recognize it? Biological recycling. Life is voracious. Dead organisms are consumed, broken down, recycled into new organisms. Bacteria, fungi, scavengers. They don't care if something was once a civilization's artifact. They just see organic matter to consume. Wood, leather, cloth, paper, food, bodies. All of it gets eaten, decomposed, returned to the carbon cycle. Only inorganic materials survive biological recycling, and even they are often incorporated into biological structures, like the calcium carbonate shells of marine organisms. All of these processes, erosion, burial, subduction, metamorphism, weathering, diagenesis, biological recycling, work together to erase the past. Not quickly from a human perspective, but inexorably from a geological perspective. A human lifetime is about 80 years. Geological processes work on timescales of millions to billions of years. That's a ratio of about 1 to 50 million. Imagine a process that destroyed 1/1,000,000th of everything you own each day. You'd barely notice at first, but after 50 million days, about 137,000 years, everything would be gone. That's what geological erasure is like, scaled to civilizations. We think our world is permanent because we live such short lives. But the Earth doesn't care about our sense of permanence. The Earth recycles everything, given enough time. This is why the Silurian hypothesis is so challenging. It's not that ancient civilizations would have left no traces. They would have left traces. Isotopic anomalies, chemical residues, extinction events. But those traces would be subtle, ambiguous, easily explained away as natural phenomena. To recognize them for what they are, you'd need to be looking for them. You'd need to know what to look for. You'd need to consider the possibility that not every mass extinction, not every carbon isotope excursion, not every mysterious event in Earth's history was purely natural. We don't do that. We assume natural causes by default. And usually, we're right. Most events in Earth's history were natural. But could some of them have been artificial? Could some of them have been us? Or something like us? The honest answer is, we don't know. We might never know. And that uncertainty is what makes the Silurian hypothesis so fascinating and so troubling. The Earth doesn't preserve history, it destroys it, continuously, systematically, thoroughly. Erosion grinds mountains to dust. Rivers carry that dust to the sea. The sea floor accumulates sediment, but then it's subducted back into the mantle at tectonic plate boundaries. What goes down doesn't come back up, at least not in recognizable form. It gets melted, mixed, reconstituted into magma that eventually erupts as new rock. The average piece of ocean floor is less than 200 million years old. There's nothing older because it's all been recycled. Continental rocks can be older, some are 4 billion years, but they're constantly being eroded, metamorphosed, remelted. The ancient rocks that survive are rare, and they've been through a lot. Any delicate information they once contained has been cooked out of them. Fossils are flukes. For an organism to fossilize, it needs to die in exactly the right conditions, usually rapid burial in fine sediment, away from oxygen, where mineralization can replace soft tissues before they decay. This happens rarely. Most organisms leave no fossil trace at all. Even the fossils we have represent a tiny fraction of the species that ever existed. Paleontologists estimate that we've discovered fossils from less than 1% of all species, probably far less. The rest lived and died and left nothing behind. If entire species can vanish without a trace, why not civilizations? Here's an exercise. Look around the room you're in. What do you see that would survive 1,000,000 years? The walls? They're probably drywall or plaster, calcium sulfate, wood pulp, paper. These will crumble within decades without maintenance. Within centuries, they'll be indistinguishable from natural mineral deposits. The furniture? Wood rots, metal rusts, plastic. Actually, plastic might survive, sort of. Microplastic fragments could persist in sediments for millions of years, but they wouldn't look like furniture. They'd look like unusual polymer particles dispersed through rock. Electronics? The silicon chips will survive, but what about them says computer? The circuits are too small to see without magnification. The housing is plastic or metal, which will degrade. The rare earth elements will disperse. Books? Paper lasts maybe a few centuries under ideal conditions, a few thousand years if it's protected from moisture and light. 1,000,000 years? No chance. The information is gone. Your body? Bones might fossilize under extremely rare conditions, but nothing about a human skeleton says built cities and split atoms. We'd look like interesting apes, which, to be fair, is what we are. Now, multiply this exercise by your entire civilization. Everything we've built, everything we've achieved, everything we know. What survives 1,000,000 years? Almost nothing that says intelligent species lived here. And yet we leave traces. Not artifacts, traces. Chemical signatures, isotopic ratios, element distributions. The carbon we've released from fossil fuels will leave a mark in sediments for millions of years. The nitrogen cycle we've disrupted with synthetic fertilizers will leave a mark. The plutonium from nuclear testing will leave a mark. The extinction of megafauna will leave a mark. But will anyone reading those marks understand what they mean? I want to talk about the Fermi paradox, because the Silurian hypothesis has something to say about it. Enrico Fermi was having lunch with some colleagues in 1950, discussing UFOs and the possibility of extraterrestrial life. At some point, Fermi asked a simple question. Where is everybody? The question cut through the speculation. If the universe is as vast and old as we know it to be, and if life arises on even a small fraction of planets, then the galaxy should be teeming with civilizations. Some of them should be millions of years more advanced than us. They should have colonized the galaxy by now. We should see evidence of them everywhere. But we don't. The sky is silent. The stars are empty. We've found no signals, no artifacts, no visitors. This is the Fermi paradox. The contradiction between the apparent likelihood of extraterrestrial civilizations and the complete absence of evidence for them. People have proposed many solutions. Maybe life is rare. Maybe the origin of life is so improbable that it almost never happens, even given billions of years and trillions of planets. Maybe we're essentially alone. But this seems unlikely, given how quickly life appeared on Earth. Almost as soon as conditions allowed it, life was here. That suggests life is easy to start. Maybe intelligence is rare. Maybe most life never develops complex nervous systems or abstract thought. Maybe Earth got lucky with some combination of factors: large moon, plate tectonics, asteroid impacts that were bad enough to cause turnover, but not bad enough to sterilize the planet. Maybe civilizations destroy themselves. This is a dark possibility. Maybe every species that develops technology eventually develops the means of its own destruction. Nuclear weapons, engineered pandemics, artificial intelligence gone wrong, runaway climate change. Maybe we're next. Maybe civilizations are hiding. Maybe there's something out there that makes it dangerous to broadcast your existence. A predator species, a hostile superintelligence, something that destroys emerging civilizations. In this scenario, sometimes called the dark forest hypothesis, the universe is full of life, but everyone is being very, very quiet. Maybe they're here and we don't recognize them. Maybe advanced technology is indistinguishable from nature. Maybe we're embedded in a simulation, or surrounded by beings so advanced they're invisible to us. Maybe interstellar travel is just too hard. Maybe the distances are simply too vast, the energy requirements too extreme, for any civilization to actually spread beyond its home system. Maybe everyone is stuck where they started. All of these solutions have problems. None of them fully resolves the paradox. But the Silurian hypothesis adds a new possibility. Maybe civilizations don't leave traces. Think about what we've just discussed. Our civilization, with all its noise and pollution and transformation of the planet, will fade to a whisper in the geological record within a few million years. Within 100 million years, there might be nothing left that clearly says intelligent species lived here. If that's true for us, it might be true for civilizations throughout the galaxy. When we look at other planets, we're looking for signs of present life. Oxygen in the atmosphere, methane, chemical disequilibrium, biosignatures. But what if the planets we're examining hosted civilizations millions or billions of years ago? The evidence would be gone. The atmospheres would have re-equilibrated. The geological traces would have been erased. We might be looking at graveyards and seeing barren worlds. Mars, for example. Today, it's a frozen desert with a thin atmosphere. But 4 billion years ago, it had liquid water, a thicker atmosphere, possibly even a magnetic field. Conditions might have been suitable for life, even complex life. If a civilization arose on ancient Mars, would we know? The surface has been scoured by billions of years of radiation and wind erosion. Any structures would be long gone. Any chemical signatures would be faint at best. We've sent rovers and landers to Mars. They look for signs of ancient microbial life, fossils of bacteria, chemical traces of metabolic processes. But they're not looking for signs of ancient civilization. Why would they? The assumption is that Mars never developed complex life. But assumptions can be wrong. Venus is another example. Today it's a hellish greenhouse, with surface temperatures hot enough to melt lead and crushing atmospheric pressure. Certainly no civilization could exist there now. But some scientists think Venus might once have been habitable. Early in solar system history, the sun was dimmer. Venus might have had liquid water oceans for billions of years before runaway greenhouse warming made the surface uninhabitable. If so, there was time for life to evolve, time for intelligence to emerge, time for a civilization to rise and fall. The evidence would be buried under hundreds of millions of years of volcanic resurfacing. Venus periodically turns itself inside out, replacing the entire crust with fresh lava. Any ruins, any artifacts, any trace of intelligence, gone. We look at Venus and see a cautionary tale about runaway climate change, but maybe we should also see a graveyard. The Silurian hypothesis suggests that the galaxy might be full of such graveyards. Planets where civilizations arose, flourished, declined, and vanished, leaving nothing behind that we could detect. Not a quiet universe because no one's there, but a quiet universe because no one lasts. This is a different kind of cosmic loneliness than the Fermi paradox usually implies. Not, we're alone because life is rare, but rather, we're alone because nothing lasts. The universe might have been full of minds, full of cultures and histories and achievements, all of it gone now, all of it forgotten. And we're next, unless we do something different, unless we figure out how to last, unless we learn from the silence of the stars. That's the practical implication of the Silurian hypothesis. It's not just an academic question about the past, it's a warning about the future. Let me tell you 5 stories, 5 scenarios for ancient Earth civilizations. These are fiction, but they're fiction built on the scaffolding of what we know about geology, evolution, and time. Story 1. The Philosophers. 200 million years ago, during the Triassic, a species of small, agile predators began developing larger brains. Maybe they were early dinosaurs, or maybe some surviving lineage of synapsids. It doesn't matter. They were social creatures, living in groups, communicating with increasingly complex vocalizations. Over millions of years, those vocalizations became language. Not human language, they didn't have human vocal tracts, but language nonetheless. Symbols for things, names for each other, words for emotions, for abstract concepts, for things that weren't immediately present. They developed culture, stories passed from generation to generation, techniques for hunting, for finding water, for navigating by the stars. Knowledge accumulated. But they never developed technology in the way we think of it. No fire, their physiology didn't require cooked food. No metal, they never figured out smelting. No agriculture, they remained hunter-gatherers, living off the land. They had philosophy, they had art, paintings on cave walls, sculptures from bone and wood. They had religion, rituals for birth and death and the changing seasons. They had mathematics, counting systems, ways of tracking the movements of celestial bodies. But none of this left traces that would survive geological time. Wood rots, bone dissolves, paint fades. Their cave paintings, if any survived the original weathering, were transformed into unrecognizable smears by heat and pressure over eons. They went extinct during a climate shift or a disease or competition with other species. Their bodies decomposed, their songs were forgotten, their philosophy died with the last mind that held it. 100 million years later, a paleontologist finds a skull. Interesting brain case, she notes. Relatively large for the body size. Might have been fairly intelligent for a reptile. She moves on to the next fossil. The philosophers are gone, not just dead, but erased, as if they never existed. Story 2. The Bright Ones. 60 million years ago, a species discovered fossil fuels. They were mammals, probably. The extinction had cleared the field, and mammals were diversifying rapidly. Maybe they looked something like us, or maybe they were completely different. Convergent evolution is unpredictable. They found coal deposits, experimented with fire, learned to extract energy from the ancient dead. Within a few thousand years, they had machines, cities, factories. a civilization recognizably similar to ours. But they burned too fast. Their population exploded. Their climate changed. They fought wars over dwindling resources. Factions with different visions of the future clashed, and some of those factions had weapons capable of mass destruction. Within 10,000 years of their industrial revolution, they were gone. Extinction. Not gradual decline, but sudden collapse. Disease and war and environmental catastrophe all feeding on each other. The planet recovered. It always does. New species filled the empty niches. Forests grew over the ruins of cities. The oceans absorbed the excess carbon dioxide, slowly, over tens of thousands of years. 50 million years later, a geologist studies the rock layers. She finds an anomaly, a thin band of unusual isotope ratios, strange chemical residues, evidence of rapid warming followed by cooling, mass extinction in the fossil record. Interesting, she says. Probably a volcanic event, or maybe methane release from ocean sediments. I should write a paper. The bright ones burned brightly, and then they were dark. Their entire history, their art, their science, their loves and fears and dreams, compressed into a few centimeters of rock. Story 3. The Wise Ones. 100 million years ago, a species developed technology but turned away before it was too late. They had fire, metallurgy, agriculture, cities. They understood the danger of burning too much carbon. They understood the fragility of ecosystems. They made a collective choice, somehow, against all the pressures of individual self-interest, to live sustainably. Their civilization lasted 50 million years. That's 10,000 times longer than human history. 50 million years of culture, of accumulated knowledge, of slow refinement. They explored their world, mapped the continents as they drifted, studied the stars. Maybe they even visited other worlds, the moon, nearby planets. We'd never know, because any artifacts they left there have been buried by dust or eroded by radiation. On Earth, they kept their footprint light. They used renewable energy, geothermal, solar, wind. They kept their populations stable. They preserved the natural world around them, living in harmony rather than domination. And then something happened. An asteroid, perhaps. A supervolcano. A gamma ray burst from a dying star. Bad luck on a cosmic scale. They tried to survive. Maybe some of them did, for a while. But eventually the last of the wise ones died, and their civilization ended. Their sustainable practices meant they left almost no trace. No carbon spike, no chemical anomalies, no mass extinction. They'd been careful to preserve biodiversity. Their 50 million years of civilization were geologically invisible. All that remains is a vague oddity in the fossil record. Certain large animals seem to be missing from certain periods, as if something was controlling their numbers. Paleontologists attribute it to unknown environmental factors, maybe disease, maybe climate fluctuation. The wise ones survived longer than any other civilization in Earth's history, but they're just as gone as if they'd never existed. Story 4. The Departed Ones. 80 million years ago, intelligent beings saw the future. They were dinosaurs, evolved descendants of something like Troodon. They had technology, science, mathematics, and they had astronomy. They tracked the movements of objects in the sky. They calculated orbits. They predicted impacts. They saw the asteroid coming, the big one, the one that would end their world. They had time, millions of years, and they used it. They developed space travel. Not easy, not fast, but eventually they got there. They colonized the Moon, then Mars, then the moons of Jupiter. They spread through the solar system, becoming independent of their home world. When the asteroid hit, 76 million years ago, they watched from space. They mourned, but they survived. On Earth, their civilization was obliterated. Cities buried under ash and debris. Artifacts melted, crushed, erased. Within a few million years, no trace remained. The planet recovered, mammals rose, and eventually a new intelligent species evolved. Us. The departed ones might still be out there. They've had 80 million years to spread and evolve. They might be in other star systems by now. They might be watching us, their distant cousins, struggling to avoid the same mistakes they made. Or they might be long extinct. Space is vast and dangerous. Civilizations can fall anywhere, not just on planets. Maybe they spread too thin and collapsed. Maybe they were destroyed by some cosmic catastrophe. Maybe they evolved into something we wouldn't recognize as intelligent. Either way, we have no evidence they existed. Their legacy on Earth was erased. And if they're out there, they're not talking to us. Story 5. The Strange Ones. They weren't like anything we can imagine. Maybe they were colonial organisms, like coral reefs but intelligent. Each individual was actually a network of billions of cells distributed across kilometers of ocean floor, thinking thoughts at a glacial pace. Their longest sentences took centuries to complete. Maybe they were microscopic, building civilizations on the scale of bacteria. Their cities were biofilms, their technology was biochemical, their wars were fought with enzymes and antibodies. They lived and died in a world we can't see without electron microscopes. Maybe they existed in the deep ocean or deep underground, in environments we've barely explored. Maybe they were chemosynthetic, deriving energy from geothermal vents rather than sunlight. Their world was darkness and pressure and heat. Maybe they weren't based on carbon at all. Maybe they were silicon-based or something else entirely. Maybe they existed only briefly, during some window of unusual planetary chemistry that closed long ago. The point is, we're looking for civilizations like ours. We're looking for our kind of traces. But intelligence might take forms we can't anticipate. The strange ones might have lived and died, and we might be looking directly at their remains without any clue what we're seeing. That unusual mineral formation might be a city. That odd isotope ratio might be industrial waste. That fossil we can't quite classify might be a tool. We don't know what we don't know. That's the deepest lesson of the Silurian hypothesis. It's not just that ancient civilizations would leave few traces. It's that the traces they left might be unrecognizable. The past is a foreign country, and deep time is a foreign universe. I've been presenting this as a mystery, but it's also a mirror. The Silurian hypothesis isn't really about what came before us. It's about what comes after. Everything I've described, the erosion, the subduction, the forgetting, will happen to us, is happening to us, right now, one day at a time. The cities we're building are already decaying. The art we're creating is already fading. The knowledge we've gathered is already being lost at the edges. We fight against this. We build monuments, we write books, we store data. We tell ourselves that we're creating something permanent, something that will outlast us. But permanent is an illusion. Nothing is permanent. Not mountains, not continents, not species, not stars. The only question is how long. Human civilization is maybe 10,000 years old, depending on how you count. Industrial civilization is 250 years old. The digital age is 50 years old. We're babies. We've barely begun. And already we're in trouble. Climate change, nuclear weapons, engineered pathogens, artificial intelligence. Any of these could end us within centuries. If we end ourselves soon, we'll leave that thin layer I described. A few millennia of anomalies. A geologist's puzzle. Interesting event here, probably volcanic. But maybe we won't end ourselves. Maybe we'll figure it out. Maybe we'll solve climate change, avoid nuclear war, align our AI, cure our diseases. Maybe we'll spread to other worlds, back up our civilization, ensure that even if Earth is destroyed, humanity continues. In that case, how long might we last? The dinosaurs lasted 170 million years, and they weren't even trying. They weren't consciously working to survive. They just existed until the asteroid. If we're trying, if we're actively working to survive, to spread, to persist, could we last 1 billion years? 10 billion? Until the sun burns out and beyond? Maybe. There's no physical law against it. The universe permits long-lived civilizations. Whether we become one is up to us. But here's the thing. Even if we last 1 billion years, we'll eventually end. Everything ends. The sun will expand, the stars will burn out, the universe will run down. Entropy always wins. So the question isn't whether we'll be forgotten. We will be. The question is what we do between now and then. The Silurian hypothesis forces us to think about timescales we usually ignore. It makes the present both more precious and less permanent. It reminds us that we're part of something much larger than ourselves, a story that started long before us and will continue long after. That story might have chapters we'll never read, civilizations that rose and fell before the first ape existed, minds that looked at the same stars we see and wondered the same things we wonder. Or maybe we are the first. Maybe intelligence is rare, precious, a cosmic anomaly. Maybe we're the universe waking up for the first time, looking at itself, asking questions no one has ever asked before. Either way, we have a responsibility to survive, to spread, to preserve what we can for as long as we can. Not because we'll last forever, we won't, but because lasting matters, because knowledge matters, because experience matters, because whatever mind comes after us, human descendants, artificial intelligence, alien visitors, or something we can't imagine, deserves to inherit something more than chemical signatures in ancient rock. We can't stop the universe from forgetting us eventually, but we can make the universe remember longer. We can be the wise ones rather than the bright ones. We can be the departed ones, spreading beyond one fragile world. We can leave traces not just in rock, but in the structure of the cosmos itself, in other civilizations we might someday contact, in descendants that carry our legacy to the stars, in knowledge that might, somehow, against all odds, survive. Or we can be the philosophers, living well, thinking deeply, creating beauty, and then vanishing without a trace, our existence known only to ourselves. There's dignity in that too. The universe doesn't owe us memory. Meaning doesn't require witnesses. But I think we want to be remembered. I think there's something in us that rebels against the idea of total erasure. We want to matter beyond our lifetimes. We want to leave a mark. The Silurian hypothesis tells us how hard that is. How many civilizations might have wanted the same thing and failed. But it also tells us it's possible. Because here we are, wondering about them. Here we are, asking questions. Here we are, alive and thinking and planning. We exist. That's something. That might be everything. And now we know the stakes. Now we know how brief our window is, how fragile our legacy, how demanding the universe is of anything that wants to last. What do we do with that knowledge? That's the question. Not whether ancient civilizations existed, but what their existence, or their erasure, means for ours. So here's my question for you. It's late at night. You're lying in bed, looking at the ceiling, thinking about everything I've said. 66 million years. Erosion and subduction. Traces that fade. Civilizations that might have been. And you ask yourself, what do I do with this knowledge? Do you despair? The universe doesn't care. Nothing lasts. Why bother? Or do you feel something else? A strange freedom, maybe? If nothing lasts, then you don't have to worry about legacy. You can focus on now, on the people you love, the work you find meaningful, the moments of beauty that light up your life. Or maybe you feel connected to the earth, to deep time, to whatever minds might have existed before you and might exist after. You're part of something vast and ongoing, even if that something is anonymous. Or maybe you feel challenged. If civilizations can be forgotten, then making a lasting mark is the ultimate achievement, the hardest thing, worth trying, even if it's probably impossible. I can't tell you how to feel, but I can tell you this. The Silurian hypothesis changed something in me. It made the present more vivid. It made the past more mysterious. It made the future more open. We don't know if we're the first. We probably can't know. But we know we're here now, asking the question. That's something. That might be everything. The rock beneath your feet is 4.5 billion years old. It's seen things we'll never know. It's held beings we'll never meet. And one day, it will hold whatever trace remains of you. What will it say? What do you want it to say? Think about that, and then go live a life worth whispering about, even if no one's listening. Even if no one ever knows, especially then. The universe wanders through us. It wandered before, it will wander again. Be part of the wandering. That's all any of us can do. That's all any of us have ever done. And maybe that's enough.